Let's talk about ionic bonding now. And of course, in ionic bonding, we have a transfer of the electron. So we'll take an example here of sodium chloride. Lewis structure-wise, I have Na, and it has 1 valence electron. Cl, and Cl, chlorine, has 7 valence electrons. And what happens when they bond? Well, we get Na. We'll draw brackets around Cl, put the minus sign. We put a positive sign, so minus there, positive for sodium, right? Because sodium gave up the electron to chlorine. And I'll keep it color coordinated there. That's sodium chloride. Remember the element symbol. That represents the noble gas core. So sodium now has 1s2, 2s2, 2p6, just like neon. So it's isoelectronic with neon. Chlorine is now isoelectronic with argon. So they both have a noble gas electron configuration, very stable. The balanced equation of this is sodium, which happens to be a solid metal, plus 1/2 of chlorine, which is a gas, goes to sodium chloride, which of course is a solid. So when this forms, we have something that we will learn later on called delta HF, which is basically heat transferred when this forms. It's called the enthalpy of formation. And that happens to be negative 411 kilojoules per each mole of sodium chloride produced. Since this is negative, this means heat is released out, which means that making sodium chloride is more stable than having sodium and metal and chlorine gas. So how do we calculate this? How do we know this? Well, we can approximate this process by using the boron hybrid cycle. Again, sodium metal plus 1/2 Cl2 goes to NaCl solid. So what's physically happening? If we go back up top here, this electron from sodium is going to chlorine. So it's an electron transfer reaction. Sodium is going to do that. Now we have a term for the energy required to remove an electron from an isolated atom or ion, and that's ionization energy, but it's the energy required to remove the electron from an atom or ion in the gas phase. We are in the solid phase. So the very first step we have to do, step 1, is we have to sublime, have a solid go to a gas, sodium, which can be done. And that happens to be 108 kilojoules per mole of energy is required to do that. That's a gas. Then sodium will give up the electron. Ionization energy. And for sodium, it's 496. This is step 2. 496 kilojoules per mole. And we have Na+. Well, chlorine. Let's look at chlorine now. The chlorine comes as Cl2. It's a diatomic element. We only want Cl, so we have to break the bond. So if you look, the bond energy for Cl2, so step 3 here, we have to break bond. And that's 1/2 of 243 kilojoules per mole. So then we get Cl gas. We had to break up Cl and Cl to just 1 Cl. It's half of that because we only want 1 Cl. Now Cl is going to gain an electron to go to Cl minus gas. And we have a term for that called electron affinity. Electron affinity, step 4. And that for chlorine gaining an electron, they get 349 kilojoules per mole. Last but not least, when sodium and chloride get together, step 5 is the lattice energy. And this is the energy released, or the energy change, let's say, associated with the formation of a crystalline lattice of alternating cations and anions from the gaseous ions. And how lattice energy would be calculated is we would use that enthalpy of formation, delta HF for NaCl, and would equal all the steps. Step 1 plus step 2 plus step 3 plus step 4 plus step 5. And what are the steps again? Well, the first one was sublimation. The second one we said was ionization energy. Third one was bond dissociation. Fourth one was electron affinity. And the last one, 5, was the lattice energy. Excellent. So if we were to do this, the lattice energy, or the enthalpy of formation is negative 411 kilojoules per mole. And that would equal sublimation, which is 108 kilojoules per mole, plus the ionization energy of 496 kilojoules per mole, with the 1/2 of the bond, which is 243 kilojoules per mole, added to the affinity of negative 349, plus the lattice energy. So that means the lattice energy of NaCl is equal to negative 788 kilojoules per mole. And that's how much energy is released when sodium chloride forms from the lattice energy. Overall is negative 411. So lattice energy is pretty negative. It's pretty favorable. So why? So lattice energy depends on 2 factors. Those 2 factors are ion size and ion charge. As for size, as radii increase, lattice energy becomes less negative. Ion charge, as charge increases, whether it be more positive or more negative, as it increases, lattice energy becomes more negative. And why that is has to do with Coulomb's law. So that's Coulomb's law, 1 over 4 pi epsilon sub 0 times Q1, the charge of first object, the first atom, Q2, charge of the second one, divided by the radius. So if we have two atoms, cation, which is relatively small, and an anion that's relatively big, the radius, R here, will be from the nucleus to the nucleus. That's technically R. So that's R. So as R gets smaller, the overall energy, or the force of attraction, gets bigger. That's just how that works. As the Q's get bigger, E gets bigger. So as ion size gets smaller, E gets bigger. As R gets bigger, E gets smaller. As charges, as Q's go up, E goes up. Q's go down, E goes down. And that's basically all we're going to talk about with ionic compounds.